In this problem, we're trying to find the rate constant at 25 degrees Celsius based on the energy of activation and the rate constant at a different temp. Additionally, find the value for A. Go ahead and give this a try, and then come on back. All right, if you're back, remember that your rate constant is equal to A, e to the activation energy over RT, which we can break down into the ln of K is equal to the ln of A minus EA over RT. When we relate two different temperature values for this, though, we can get an equation that says that the natural log of K2 over K1 is equal to the negative activation energy over R times the difference of the reciprocals in the temp, 1 over T2 minus 1 over T1. This energy and temp relation to the natural log of the ratio of our constants is something we see often, and we can use here for rate constants as well. So what values do we know? Well, we have a K forward already. We'll say that's K1. We had a temp for it. It was 0 degrees Celsius. We know the temp of where we want to be, so we'll call that T2. We want K2. We were given energy of activation, R is a constant. So there's only one thing we don't know, and that's the rate constant at the temp we want. Setting things up then, natural log of K2 minus the natural log of K1, or the natural log of 5.2 times 10 to the 6. That is going to equal negative activation energy, so negative 6,200 joules per mole over 8.314 joules per mole Kelvin, times 1 over T2, well, these have to be in Kelvin, so 25 Celsius, 298 Kelvin, minus the original 0, 273 Kelvin. We'll find that the natural log of K2 minus 15.4642 is equal to 0.229162. Add 15.46 to both sides. The natural log of K is going to be positive 15.6933. E to both sides. Our K at 25 degrees Celsius is going to be 6.54 times 10 to the 6. So we can find the rate constant at our higher temperature if we know the energy of activation and a reference rate constant and temperature.